Okay, so here we assumed we have these better word vectors, but now let's look at how we can actually get vectors that are not high dimensional like the ones before, but capture these meanings here. So obviously we could make some vectors by hand manually. For example, we want to create vectors in a three-dimensional vector space where one dimension is about how much the word is about pets, the second, how much it is about animals, and the third dimension is how much it is about cities. Remember a couple of lectures ago, we had this vector space of movies, again with 3 dimensions, and we looked at where can we put a movie in 3 dimensions where one was cartoon, one was aliens, and one was basketball. And then each movie would go somewhere in this vector space of these 3 dimensions. And here we do the same thing. We manually decide the word cat, where should it go in the 3-dimensional space of pets, animals, cities. So obviously the cat has nothing to do with cityness. So we give it a value of 0 in the 3rd dimension. But it has a lot to do about pets, and it has something to do about animals. So this would be its position in the vector space of these 3 dimensions. Then for the dog, we do almost the same thing, except we say dogs also run around in cities, unlike cats, which stay at home. So we have a slightly different value for the cityness of the dogs. Then we take an apple. An apple has no petness at all, but apples appear in the city. So we decide on this vector representation for an apple. Lions, again, not a pet, shouldn't really have a lion at home, even though some people do. Not mentioning the Netflix series here. But obviously lion is a lot about animals and it might appear in the city in the zoo. New York City, on the other hand, here we give it a negative value for petness and give it a high value for cityness. So you can see we can manually decide what the dimensions are, and then we can make a word vector by manually defining the value for each of these 3 dimensions. And now if we do this, we end up with a 3-dimensional vector space, and we can visualize each word in these 3 dimensions here. So you can see cat and dog have slightly different vectors, but in this vector space, they are rather close to each other. So you can see a small cosine, high cosine similarity. On the other hand, if you look at New York City and cat, this is going to be a huge distance between them. So this is all nice and good, but again, it would not be practical to do this manually for first hundreds of thousands of words, and second, deciding what these dimensions really are. You could come up with some of them, but for comprehensive classification in maybe a few hundred dimensions and do this for documents with millions of words, you cannot do this manually. However, there is a way to calculate these automatically. And there was a guy, Thomas Mikolov, who had an intern job at Microsoft. He came up with the idea to train a neural network to compute exactly these type of word vectors. How the calculation works, I'll show you in a minute. But what happened is, he figured this out while being an intern. He graduated. He was quickly hired by Google. And then a year later, 2013, he published a library called Word2Vec, doing these calculations as an open source library. So nowadays, these word vectors is what's known as word embeddings. And typically, you calculate them with a few hundred dimensions. So this is very different from TF-IDF vectors, for example. Remember there, the vector is the size of the vocabulary, which can be thousands of dimensions. So here, this is way smaller. So something like typically around 300 dimensions. And to make this work well, you'll see you have to train this on a large number of words. So one corpus this is typically being trained on is, again, published by Google, a news corpus which has 100 billion words. And then if you train this on 100 billion words, you get very nice word vectors out of it. So this is using neural networks. Again, I'll show you how exactly in a minute. But an important point is that we are using a network that is doing unsupervised learning. So we don't have to tell it what we expect as the output. That would be pointless because this is exactly what we want to figure out. If we already knew what the vectors looked like, we didn't have to calculate them. So we're going to use a form of unsupervised learning with a network architecture that's called an autoencoder. But going back to the word math, so again, simplify to 2 dimensions because it's difficult to draw 100 dimensions. If you have this kind of analogy question, you can visualize each word vector in this vector space here. You know, like the vector for what we had earlier with Louis Pasteur, or on the worksheet with the food examples. So now, if you want to know how Seattle relates to the Seattle Sounders as Portland relates to what else, we can do this with the vector space calculation. So in this example here, we start from Seattle, the city. We add a sports team from Portland. Now, so you can see the vector for Portland Timbers we are adding up here. Now we are adding in the vector space in this point here. But now we want to know what the corresponding example is from Seattle. So we subtract the vector for Portland. So that's the vector here. We subtract it, we get to a point in space here. And then in this point in the vector space, we are going to find the Seattle Sounders sports team. So in real, this wouldn't just be in 2 dimensions. We would do this on these word vectors, which have typically, again, 100, 200, 300 dimensions, but it's the same calculation. We are adding the vector, subtracting one, and then get a result vector here. So obviously in the result in the vector space, we are not going to find a vector that has exactly these values, but we can look again using cosine similarity, what are the closest ones, and then pick the closest one or the closest 1 or 2 as the answer for the question. And people have been doing all kinds of fun things with these word vectors. For example, there are various ways to project these high dimensional vectors into a smaller number of dimensions. So again, we are using word vectors, which have maybe 300 dimensions, but based on different mathematical techniques, you can reduce the dimensions for like a 2D or 3D visualization. And here we are doing this with all the word vectors for cities in the US. And you can see that, for example, the word vectors that we computed for Houston and Dallas are very close to each other because the cities are so similar. Remember, these are calculated from news. So the way these words appear in the news are very similar. Likewise, cities like LA, San Jose, San Diego are very close in this vector space and very far from other cities like Chicago. Okay, how can we compute these vectors automatically? How does this word-to-vec model work? Well, you'll see there are basically 2 different approaches in computing these vectors. I'll show you both. The actual training is the same, just the way we feed the input is slightly different. One is called a skipped gram, and the other is a CBOW, a continuous bag of words. In practice, what you can do nowadays is you don't have to necessarily train this from scratch. You can just download these pre-trained word embeddings for many domains. And again, one famous one is the word-to-vec model that was trained on the Google News articles. But people have been training this on all kinds of documents. So obviously, if you don't use news, but you use medical documents, you're going to get different word vectors out of it. People have been also building this on all kinds of other corpora. So there are word vectors for Harry Potter, for Lord of the Rings, basically anything you can come up with, and you have electronic documents, people build these word vectors for. Later, I'll show you how you can work with word vectors in spaCy, the NLP library we are using, and I'll show you another model that comes from Facebook as well. But first, let's see how you can train it, and we'll start with the skip-gram approach. So as training data, we have documents. So in this case, we have a sentence: Claude Monet painted the Grand Canal of Venice in 1908. So now what we do is we take this input sentence here, and we are producing a so-called skipgram. So this is the word surroundings. In this case, we're using bigrams. So we have Claude Monet and the Grand, so two words together. And we want to be able to predict from these surrounding words which word goes in here. So given Claude Monet and the Grand, we want to be able to predict that the word that should go in here is painted. Wait, what did I just say? I think I just switched input and output around. So obviously, the input word is painted in this approach. So we are feeding in painted, and we want to predict the surrounding words. So when the word is painted, we want to predict Claude Monet, the Grand. And for example, if the input word is the, we want to be able to predict Monet painted Grand Canal, and so on. So the goal is to predict the surrounding words of a given window. In this example, the window is 2, based on the input word. So let's look at the complete sentence. This is our training sentence, the same one as before. And now we can create a whole series of training data for it. So because here Claude is the first word, we don't have any words before, so these ones are empty. But we can predict the 2 words after. Monet follows after Claude and painted. Then for the next word, Monet, again, we don't have 2 words before it, but we can predict the word just before Monet. We expect that there is Claude. And after we have painted the, and this goes on and on. Now we actually have the one that we've seen here. So for the input painted, we want to predict Claude Monet, the Grand, and so on and so on. So we're going through, we're going to slide these windows across the whole sentence and have these 10 training samples. Now we can feed them into a neural network. And how does this look like? So we are encoding the input as a one-hot vector. So the input is a single word. Again, this is the word that we put in as input here, like Claude, Grand, Venice. So we are encoding this as a one-hot vector. So exactly this word here has a 1, and all the other words have a 0. And then we have again a hidden layer with n hidden neurons. And here is where the magic happens. Remember, I told you we have around 100, 300 dimensions for these word vectors. So this is exactly the number of hidden neurons here. For example, if you want to have word embeddings in 100 dimensions, we have 100 hidden neurons here. And then the output is exactly what we want to predict. So for example, Claude Monet painted the. So we want to have values for that correspond to the training sample here. So for painted, it's Claude Monet, the Grand. So here in the output, so first the calculation is just as we've done it before. We have weights for each of these input connections from the input one-hot vector to the hidden neurons, and then again from the hidden neurons to the output vector. One difference is the way we calculate the output here, which is typically done with softmax. So the main idea of softmax is that when you compute the output vector here, because you can have all kinds of weights here, the output values can be all over the place. Can be some large values, some small values. And with softmax, we can basically normalize them into an interval between 0 and 1. So this is the formula. This is going to be calculated, where E is Euler's number. And once you've done this, you have an output vector where all the values add up to 1. And you'll see this is very typical as an activation function in the output layer of a neural network. So just to see how this softmax works and get a bit of feeling for it, there is a small exercise on the worksheet. And once you're done, I'll see you back for the next part of the word-to-vec calculation.